Welcome to our Quantum Deep Dive. Today we're diving into something really mind-bending, ghost imaging, or GI. I mean, think about it, forming a sharp image of something without directly shining light on it. It sounds like pure sci-fi, right? But it's a real imaging technique, and it's already making waves in fields from medicine to security. Our guide for this deep dive is a fantastic essay by Jorgo Schneeppel titled Ghost Imaging, GI, Bildgebung mit Quantenlicht. So our mission today is to unpack this amazing tech and, show you how it challenges our everyday ideas about seeing.
It really is a different way of thinking about imaging, completely different, because at its heart, ghost imaging doesn't build a picture from light that bounced off an object directly. Instead, it relies on these subtle correlations, often quantum correlations, between different light beams. And this indirect method, well, it just opens up possibilities in situations where normal cameras are useless. Think thick fog, super low light, maybe even looking through certain material.
Okay, wow. My intuition is already struggling, which I love. So you said correlations, not direct light. Can you break that down a bit more? How on earth can you image something you're not directly looking at?
Right. The core idea is the correlation between photons or light particles. The key thing is this. You can reconstruct an image even if only one beam of light actually interacts with the object. The other beam, which is correlated, linked to the first one, never actually touches the object. So imagine splitting a light source. Beam 1, the signal beam, hits the object. Beam 2, the reference beam, takes a totally different path. The image comes from comparing or correlating what those two separate beams detected.
That sounds completely backwards. So how is that fundamentally different from, say, my phone camera? Or even an X-ray? Don't those need the light or radiation to hit the thing they're imaging?
Yeah, exactly. Conventional imaging, your camera, an X-ray machine, it all works by detecting light or radiation that's passed through or reflected off the object. You capture that direct interaction. Ghost imaging, though, it's different. It works based on statistical properties and often quantum mechanics. Things like quantum entanglement, where particles stay connected over distance, or even just strong classical correlations. The big difference, the key differentiator, is that the actual picture, the spatial information, comes from the reference beam, the one that never saw the object. And that's why it's so powerful in tricky situations where direct light might be impossible or damaging.
Okay, fascinating. So this idea that this indirect imaging, when did it first pop up? Have we been doing this ghost seeing for long?
Well, the theory and the first experiments, they really emerged in the 1990s, some groundbreaking work by T.B. Pittman and his colleagues. But what's really interesting is how it developed. Initially, GI was all about entangled photons. These are pairs of photons created together, often through a process called SPDC, spontaneous parametric down conversion. They're deeply linked.
Right.
But then later research showed, hey, you can actually get this to work with classically correlated light too. Light that has correlations but isn't necessarily quantum entangled. And that really broadened its potential uses quite a bit, made it more versatile.
Okay, this is where it gets really interesting for me. How do these ghostly correlations actually work day to day in a lab? I mean, we're talking about extracting an image from almost nothing, it feels like. Can you walk us through the physics?
Absolutely. So the deep physics, especially for the quantum version, relies on quantum correlations and entanglement. Think of two photons created at the exact same moment, linked in some way. Maybe their polarization, maybe their momentum. Even if they travel far apart, measuring something about one instantly tells you something about the other. It's that famous spooky action at a distance.
Spooky action, right.
GI uses this. We often use SPDC, like I mentioned, where one high-energy photon splits into two lower-energy ones that are correlated. This connection lets us get image information, even if only one photon of the pair hits the object. The other photon, the one that missed the object, it acts like a witness. It carries the spatial map, you could say. Now, importantly, while it started quantum, people realized you can achieve similar results with classically correlated light. This might be light where the intensity fluctuates randomly, but in a correlated way between the two beams, or where you artificially pattern the beams. So it's this really neat bridge between classical and quantum optics.
That's clear. Thank you. So if I wanted to build one of these setups, hypothetically, of course, what would I need? What does a ghost imaging system actually look like?
Well, conceptually, it's not too complicated, though the parts need to be very precise. You start with your light source, splitting it into the signal beam and the reference beam. The signal beam goes towards the object, interacts with it, passes through, reflects off, whatever. And here's a key part. That signal beam then hits a detector that doesn't form an image. It's often called a bucket detector.
Bucket detector.
Yeah, it just measures the total amount of light, the total intensity that gets through or reflects off. No spatial information at all from that beam's detector. Okay, meanwhile, the reference beam, it travels its own path, completely missing the object, and it goes to a high-resolution detector, a good camera, essentially, that can map out the reference beam's pattern in detail. The ghost image then appears when you mathematically correlate the readings. You correlate the total intensity from the bucket detector with the spatial patterns recorded by the reference camera, measurement by measurement. It's like putting together clues. The bucket tells you something got through here, and the reference camera tells you, and the light pattern looked like this at that exact moment. And for the quantum version, yeah, you often need specialized single photon sources to get those really strong correlations. Plus, you need incredibly sensitive detectors, maybe like superconducting nanowire single photon detectors or SNSPDs. These can count individual photons, which is crucial, especially if you're working with very faint light. And then there's the statistics. Because you're building the image from correlations over many, many measurements, statistical methods are absolutely vital. You need clever ways to pull the signal out from the noise. And this is where modern computing comes in big time. Machine learning, AI algorithms. They're becoming essential for reconstructing images faster and better, especially if the data is noisy or you don't have all the measurements you'd ideally want.
Right? AI seems to be everywhere. So, okay, we have this amazing, somewhat spooky technology. What does it actually mean for us, for you listening? Where is ghost imaging being used now? Or where might we see it pop up in the future? It sounds like it could change a lot of things.
Oh, definitely. The applications are really broad and often tackle problems other methods can't touch. Take medical imaging. GI offers a potential way to get high-quality images with much, much lower radiation doses.
That's huge.
It is. Think about scans for children or frequent monitoring. Being able to use extremely low light or minimal X-rays is a game changer. AI can then help clean up those low-dose images too, and there's real potential in tomography, like for CT scans. Using correlated beams could allow detailed 3D reconstructions with significantly less radiation hitting the patient. Then there's security and surveillance. GI's knack for seeing through scattering media like fog, smoke, maybe even thin walls in some cases is obviously very attractive.
Say through a wall. There, now it's really sci-fi.
Well, certain kinds of walls or scattering materials, yes. It's perfect for challenging environments, maybe disaster response or military uses. And another thing, invisible illumination. You could use an infrared or UV signal beam invisible to the eye, but keep the reference beam in the visible spectrum so you can image something without anyone knowing it's being illuminated. Very useful for discrete surveillance. In industry, GI is great for non-destructive testing, material testing, and quality control. It can spot hidden flaws or differences inside materials without cutting them open or damaging them. Think aerospace parts or complex electronics.
Yeah.
It can also be used in optical sensors to measure surfaces very precisely, even if there's a lot of stray light or the conditions are difficult, maybe for real-time checks on a production line. And finally, fundamental research. GI itself is a fantastic tool for probing quantum mechanics, studying entanglement and correlations. It helps us understand the quantum world better. And in astronomy, it could help us peer through interstellar dust clouds or gas to see objects hidden behind them, maybe observe faint signals from the early universe or exoplanets more clearly.
Okay, the potential is just staggering. It really does sound almost magical. But, even magic has its limits, or maybe its tricks. What are the big hurdles? What advancements are happening now? And what challenges does GI still face before it's, say, in every hospital or factory? What's the catch?
You're right, there are definitely challenges. On the hardware front, things are improving fast. Detectors are getting much better lower noise, higher efficiency, which means better images, light sources too. We're moving beyond just lasers and traditional SPDC sources to things like quantum dots and, importantly, integrating components onto photonic chips. That's key for making systems smaller, cheaper, and more robust.
Right, miniaturization.
Exactly, and this ties into the growing role of broader quantum technologies. Using entanglement isn't just for imaging, it improves precision and could even link up with quantum communication or cryptography. And on the software side, the algorithms, AI, and machine learning are making a huge difference. Neural networks, generative models, they can reconstruct images from less data or noisier data much more effectively than traditional methods. It makes GI more practical. Plus, there's ongoing work on just smarter ways to analyze the data, improve that crucial signal-to-noise ratio, maybe using adaptive techniques or advanced noise filtering. But the challenges remain. One is the ultimate resolution and image quality. It's limited by physics, the coherence of the light, the detector pixel size, noise levels. We're pushing those limits, but they exist. Getting images in real time can also be tough because correlating all that data takes significant computing power, especially for complex scenes. And probably the biggest barrier right now is the complexity and cost. Setting up a GI system needs precise alignment, careful calibration, and often expensive specialized components like those single photon detectors. That makes it hard to just roll out everywhere commercially.
Okay, that makes sense. So looking further ahead, painting with a broad brush, what's the ultimate vision? If we overcome these hurdles, how could ghost imaging reshape things in the next, say, 10, 20 years?
Well, the vision is pretty exciting. We'll likely see brand new applications emerge. Think about environmental monitoring, using GI to map pollution plumes in the air, or maybe monitor ecosystems in murky water, or detect gases remotely in hard-to-reach places. And perhaps molecular imaging at a new level, getting detailed views of biological structures, maybe even without needing fluorescent labels, using very low safe light levels. That could be huge for biology and medicine. But the really transformative potential, I think, lies in integrating GI with other powerful technologies. Imagine pairing it with quantum computers. They could potentially crunch those complex correlation calculations almost instantly, enabling real-time GI for dynamic things, like tracking movement during surgery or monitoring fast industrial processes. Quantum algorithms might find entirely new ways to extract information, too. And synergies with photonic chips, as I mentioned, putting entire GI systems onto small integrated chips. That opens the door to portable, maybe even handheld devices for security, environmental checks, point-of-care medical diagnostics. So the vision for the next decades. I think ghost imaging could transition from being a somewhat niche, high-end technique to becoming a standard tool in many scientific and industrial toolkits. From labs to factory floors to hospitals, the societal and economic impacts could be really significant. Better healthcare, maybe new tools to fight climate change, new high-tech industries and jobs. It could really spur innovation.
What an incredible journey through the world of ghost imaging. It's so clear this isn't just an incremental improvement. It's a fundamentally different way to see. The potential truly feels vast. It makes you wonder, doesn't it? As we merge techniques like this with powerful AI, maybe even quantum computing, are we heading towards a future where our current way of seeing things directly feels almost primitive? Will we look back at today's cameras like we look back at, pinhole cameras?
That's a fascinating thought. Ghost imaging really does sit at this intersection of classical and quantum ideas about light and information. It's incredibly versatile, and its ability to work in challenging conditions, potentially with lower costs and higher sensitivity, thanks to integration and AI. While it means it's poised to make a real difference across research and industry, it's definitely changing how we think about capturing information of the world around us.
Well, thank you so much for guiding us through that. And thank you, our listeners, for joining this deep dive inspired by Yorgo Schneppat's insightful essay on ghost imaging. If you want to explore this further, you can find more information and related work over at schneppat.de.
Goodbye for now.
Goodbye.